Time is not a thing you can touch, only a way to describe change. When Richard Feynman talked about time, he challenged one of the most natural assumptions humans make, that time is a physical thing. In everyday language, we treat time almost like an object. We say we save time, lose time, or feel that time is passing. But according to physics, and especially the way Feynman explained it, time is not something that exists on its own. It is not a substance, an energy, or a force. Time is a concept we use to describe how things change relative to one another. To understand this, imagine a universe where absolutely nothing changes. No movement, no vibration, no growth, no decay. In such a universe, asking how much time has passed would be meaningless. Without change, there is no way to define before or after. Time only becomes meaningful when something happens. This shows that time depends on change, not the other way around. Feynman emphasized that what we really observe in nature is motion and transformation. The hands of a clock move, atoms oscillate, hearts beat, planets orbit stars. We choose one regular repeating motion, like the vibration of cesium atoms, and use it as a standard. Then we compare all other changes to it. When we say 1 second has passed, what we actually mean is that a chosen process has completed a certain number of cycles. Time, therefore, is a measurement system, not a physical entity. This idea becomes clearer when we think about clocks. Many people believe clocks measure time itself. In reality, clocks only measure change. A pendulum clock measures the swinging of a pendulum. A digital clock measures electronic oscillations. If a clock breaks, time does not stop. Only that particular method of tracking change stops. This proves that time is not inside the clock. The clock is simply a tool we use to label change. Feynman also pointed out that because time is a description rather than a thing, it does not behave the way objects do. Time cannot flow like water, speed up like a car, or slow down like a tired runner. When we say time flies, what we really mean is that many changes happen quickly compared to our expectations. When we say time drags, it means few noticeable changes occurred. These are psychological experiences, not properties of time itself. This understanding helps clear confusion about modern physics. In relativity, we say time runs slower for fast-moving objects or in strong gravity. This does not mean time itself is stretching or shrinking like rubber. It means that physical processes, such as atomic vibrations, occur at different rates under different conditions. Since time is defined by those processes, it appears to change. The key point is that change determines time, not the other way around. By explaining time this way, Feynman removed much of its mystery. Time is not a hidden force controlling the universe. It is a powerful human-made framework for organizing observations. It allows us to predict events, compare processes, and understand cause and effect. But it has no independent existence apart from change. In the end, seeing time as a description rather than a thing frees us from false assumptions. It reminds us that physics is not about comforting ideas, but about accurate ones. Time does not exist to move us forward. We move, we change, and time is simply the language we use to describe that endless transformation. Physics treats time differently from everyday human experience. In daily life, time feels simple and familiar. It seems to move in one direction, at one steady pace, the same for everyone, everywhere. We wake up, grow older, remember yesterday, and plan for tomorrow. This personal experience makes time feel absolute and universal. Richard Feynman explained that while this everyday view is useful, it is not how time truly works in physics. Human experience of time is shaped by biology and memory. Our brains are designed to notice sequences of events and store them in order. Because we remember the past but not the future, time feels like it flows forward. Because our bodies change at a fairly constant rate, time feels steady. Physics, however, does not begin with feelings. It begins with measurement, comparison, and equations. In classical physics, time was once treated as absolute, just as we experience it. But modern physics revealed that this assumption was incorrect. Feynman often explained that time is linked to motion and energy. When objects move very fast or exist in strong gravitational fields, the rate at which their physical processes occur changes. Since time is defined by those processes, time itself becomes relative. This idea is deeply counterintuitive. From our perspective, a second is always a second. But physics shows that two observers moving at different speeds can measure different amounts of time between the same events. Neither observer is wrong. Each is measuring change within their own frame of reference. Time is not a single universal ticking clock for the entire universe. Feynman helped people understand this by emphasizing what clocks really measure. A clock is any system that changes in a regular way. If that system is affected by motion or gravity, its rate of change will differ. This is not because time behaves strangely, but because physical processes behave differently under different conditions. Time simply reflects those differences. Another way physics treats time differently from human experience is in its equations. Many fundamental laws of physics work almost the same whether time moves forward or backward. If you film certain particle interactions and play the video in reverse, the equations still make sense. This is shocking to our everyday intuition, which insists that time must have a clear direction. In human life, the direction of time feels obvious because of cause and effect. We believe causes always come before effects. Physics shows that this sense of direction does not come from time itself, but from increasing disorder, also known as entropy. Systems naturally move from order to disorder, and this gives us the feeling of time moving forward. The laws of physics do not demand this direction, probability does. Feynman also pointed out that physics does not explain why the present moment feels special. Equations treat all moments equally. Past, present, and future are simply labels we attach to events. The feeling of now is a feature of human consciousness, not a feature of the universe. Physics describes what happens, not how it feels, by separating human experience from physical description. Feynman showed why time is so confusing. We tried to understand the universe using instincts that evolved for survival, not for cosmic truth. Physics forces us to let go of comfort and accept that reality does not revolve around our perceptions. In the end, physics does not deny our experience of time. It explains its limits. Our everyday sense of time works well for living, but not for understanding the universe. Feynman's insight was that to truly understand time, we must stop trusting how it feels and start trusting how nature behaves. Motion and time are deeply connected through measurement. Richard Feynman explained that time cannot be separated from motion. We never observe time by itself. We only observe things moving, changing, or evolving. Every practical definition of time is based on motion, and without motion, the concept of time would lose its meaning. This connection is not philosophical speckle. It is built directly into how physics measures reality. From the earliest civilizations, humans measured time using motion in nature. The rising and setting of the sun, the phases of the moon, and the movement of stars across the sky were all used as clocks. These systems worked because their motion was regular and predictable. Feynman emphasized that this is not a coincidence. Motion is the only thing we can reliably compare events against. Modern clocks follow the same principle. A mechanical clock uses the swing of a pendulum. A quartz clock uses the vibration of a crystal. An atomic clock uses the oscillation of atoms. These are all forms of motion at different scales. When we say a second has passed, we mean that a particular motion has repeated a fixed number of times. Time, therefore, is defined by counting motion. Feynman made it clear that this definition is not optional. There is no alternative way to measure time. We cannot point to time directly or isolate it in an experiment. We can only observe physical systems and track how their motion unfolds. This means that time is inseparable from the behavior of matter and energy. This connection becomes especially important in modern physics. According to relativity, motion affects how time is measured. When an object moves very fast, the internal motions within it, such as atomic vibrations, occur more slowly relative to a stationary observer. Because time is defined by those motions, time itself appears to slow down. This effect has been confirmed by experiments using fast-moving particles and precise clocks. Feynman stressed that nothing mysterious is happening to time. What changes is the motion of physical systems. Time simply reflects those changes. If all motion in a system slows down, then time, as measured by that system, slows down as well. This reinforces the idea that time has no independent existence beyond motion. Even our sense of time depends on motion. The human body keeps time through biological processes, heartbeats, neural signals, chemical reactions. When these processes speed up or slow down, our experience of time changes. In moments of fear or excitement, internal motion accelerates and time seems to stretch. In routine or boredom, fewer changes are noticed and time feels slow. This subjective experience mirrors the physical principle that time is tied to change and motion. Feynman also pointed out that if motion were completely frozen everywhere in the universe, time would effectively stop. Not because time has halted as an entity, but because there would be no process left to define it. Without motion, there is nothing to measure and nothing to compare. By connecting time to motion, Feynman removed the illusion that time is a background stage on which events happen. Instead, time is part of the events themselves. It is woven into the behavior of particles, planets, and people alike. This understanding reshapes how we think about reality. The universe is not moving through time, it is changing, and time is our way of keeping score. Motion is the substance, measurement is the method, and time is the result. In Feynman's view, to understand time, you must first understand motion, because without motion, time has no meaning at all. The past and future exist as relationships, not locations. Richard Feynman approached the ideas of past and future with a perspective that challenges how we normally think about them. In everyday language, we imagine the past as a place we have left behind and the future as a place we are moving toward. We speak as if time were a road and we are traveling along it. Feynman explained that this picture is misleading. In physics, the past and the future are not locations in space. They are relationships between events. When we say something is in the past, we mean that it has already influenced the present. When we say something is in the future, we mean it has not yet had an effect on what is happening now. These are relational descriptions, not physical positions. Nothing in the universe is marked with a label saying past or future. Those labels depend entirely on how events are connected. Feynman emphasized that physics describes events, not moments flowing along a timeline. An event is something that happens at a particular place with particular conditions. The relationship between events, such as which one can cause another, is what gives rise to our idea of past and future. If one event can influence another, we say it comes earlier. If it cannot, we say it comes later. This way of thinking becomes especially important in relativity. In classical thinking, everyone agrees on what events are happening now. Physics shows this is not true. Two observers moving differently can disagree about the order of events that are far apart. One observer may say event A happened before event B, while another may say the opposite. This does not break reality. It shows that past and future are not absolute locations but depend on perspective. Feynman explained that what remains consistent is causality. Causes always come before effects within any observer's frame. The relationships between events that can influence each other are preserved. This means the structure of cause and effect matters more than any universal timeline. Past and future are defined by these causal links, not by a cosmic clock. Our strong emotional connection to the past and future comes from memory and anticipation. The past feels fixed because we have records of it. Memories, photographs, physical traces. The future feels uncertain because it has left no traces yet. Physics does not assign these qualities to time itself. The universe does not remember its past or worry about its future. Only conscious beings do. Feynman also pointed out that nothing in the laws of physics requires the future to be open or the past to be closed. The equations simply describe how systems evolve given certain conditions. The distinction between past and future is something we impose based on how information flows. Thinking of the past and future as relationships rather than places removes many common confusions. We stop asking where the past has gone or where the future is hiding. Instead, we focus on how events are connected and how information moves through systems. In this view, the present is not a special location either. It is simply the set of events we are currently interacting with. As conditions change, different relationships become relevant, and what we call the present shifts accordingly. Feynman's explanation replaces the image of time as a road with time as a network. Events are nodes, and cause and effect connections are the links. Past and future are not destinations on that network. They are descriptions of how one event relates to another. Understanding this helps us see time not as a journey through places, but as a structure of relationships shaping everything that happens. Clocks do not define time, they respond to it. Richard Feynman often reminded people that it is easy to confuse the tools we use with the reality they describe. One of the clearest examples of this confusion is the clock. Most people instinctively believe that clocks define time. We look at a clock to know what time it is, so it feels natural to assume that time comes from the clock. Feynman explained that this idea is backward. Clocks do not create or define time. They simply respond to physical processes, and we use those processes to measure change. A clock is any system that undergoes regular, repeatable change. A swinging pendulum, a vibrating crystal, or an oscillating atom can all function as clocks. What matters is not the clock itself, but the consistency of the process happening inside it. When we say a second has passed, we are really saying that a particular physical process has completed a specific number of cycles. This distinction is important because it shows that time exists independently of any one measuring device. If all clocks were destroyed, events would still occur in sequence. Planets would still orbit stars, particles would still interact, and life would still change. The absence of clocks would only mean that we could no longer label those changes with numbers. Time would not vanish, our ability to measure it would. Feynman used this idea to explain why different clocks can disagree. In everyday life, we expect all clocks to show the same time. Physics reveals that T is not always true. A clock on a fast-moving spacecraft will tick more slowly than one on Earth. A clock in strong gravity will tick more slowly than one in weak gravity. This does not mean time itself is confused. It means the physical processes inside the clocks are responding differently to their environments. The clock is not telling time what to do. Time is revealing how the clock behaves. This reversal of thinking is central to understanding modern physics. Time is defined by change, and clocks are just examples of changing systems. Feynman also pointed out that if we built a clock that relied on a different physical process, it would still measure time correctly as long as the process was regular. This shows that time is not tied to any specific mechanism. It is a general concept that applies to all change. Even our bodies function as clocks. Heartbeats, breathing, and chemical reactions in the brain provide a sense of duration. When these processes speed up or slow down, our perception of time changes. Once again, it is not time itself that changes, but the systems responding to conditions. By understanding that clocks respond to time rather than define it, we avoid a major misunderstanding. We stop thinking of time as something produced by machines and start seeing it as a framework for comparing processes. Clocks are servants, not masters. Feynman's explanation teaches humility. Nature does not care about our instruments. The universe operates according to physical laws, and our devices merely reflect what is happening. Time is not written on the face of a clock. It is written in the behavior of the universe itself. This insight helps us appreciate why time can appear different in different situations. When conditions change, clocks change, and time appears to change with them. In reality, what we are seeing is the universe revealing how deeply time is connected to physical behavior. Clocks do not define time. They respond to it, faithfully recording the rhythm of change that never stops. Understanding time requires curiosity, not certainty. Richard Feynman believed that the greatest obstacle to understanding time is not complexity, but false confidence. Humans want clear, final answers. We want time to be a simple thing we can fully explain and control. Feynman argued that this desire for certainty often prevents real understanding. Time is not something to be accepted as obvious. It is something that must be questioned with curiosity. From childhood, we are taught to use time without thinking deeply about it. We learn hours, minutes, calendars, and schedules. These tools are practical, but they create the illusion that time is fully understood. Feynman warned that familiarity is not the same as understanding. Just because we use time every day does not mean we know what it truly is. Curiosity begins by admitting ignorance. Feynman often said that it is perfectly fine not to know. In fact, not knowing is the starting point of science. When we ask what time really means, we quickly discover that our common explanations fall apart. Is time a force? No. Is it a substance? No. Does it flow? That is only a metaphor. Each rejected idea opens the door to deeper questions. Physics advances not by declaring certainty, but by testing assumptions. The history of time in physics proves this. For centuries, time was assumed to be absolute and universal. That certainty felt logical and comforting. When experiments contradicted it, curiosity allowed scientists to let go of the old idea and accept relativity. If they had clung to certainty, progress would have stopped. Feynman emphasized that curiosity keeps our thinking flexible. Time behaves differently at high speeds, in strong gravity, and at the quantum level. Each discovery challenges what we thought we knew. Instead of forcing time to fit our expectations, curiosity invites us to let nature speak for itself. This attitude also protects us from false explanations. Many people claim to fully explain time using mystical or oversimplified ideas. Feynman rejected this approach. Saying time is an illusion or time is energy may sound confident, but confidence without evidence is not understanding. True understanding is comfortable with incomplete answers. Curiosity also applies to how time feels. Physics does not explain why moments feel long or short, or why the present feels special. Rather than inventing answers, curiosity accepts that human experience and physical description are different things. This separation prevents confusion and keeps inquiry honest. Feynman's approach reminds us that time is one of the deepest concepts in science. It connects motion, causality, memory, and change. Expecting a simple, final explanation is unrealistic. Curiosity allows us to explore these connections without demanding closure. In everyday life, certainty helps us function. In science, certainty can become a trap. Feynman taught that the beauty of understanding time lies in asking better questions, not in claiming final answers. To understand time is not to master it, define it once and for all, or remove its mystery. It is to stay curious about how the universe changes and how we describe those changes. Time rewards curiosity because it reveals new layers each time we question it. Certainty closes the door. Curiosity keeps it open. Thank you so much for watching. If this video inspired you, be sure to like, share, and subscribe to be inspired from life for more motivational content. And remember, no matter where you are in life, you have the power to change your future. See you in the next video.